A rock the size of a car is about to enter Earth's atmosphere at 40 times the speed of a bullet. No warning, no siren. In about 3 seconds, it will detonate with the force of 30 Hiroshima bombs. Not because it contains nuclear material, not because it carries explosives, but because it's moving fast. Pure velocity, nothing else. And here's what should unsettle you. Rocks this size pass closer to Earth than the Moon every few weeks. Statistically, one strikes every century or so. The last one hit Russia in 2013. Before that, Siberia in 1908. The pattern isn't reassuring. So how does a rock become a bomb? The answer lies in a single equation that explains everything from scraped knees to mass extinctions. Kinetic energy equals 1/2 times mass times velocity squared. You probably saw this in high school. But the non-obvious part, the part that matters, is that word squared. Double an object's speed and you quadruple its energy. Triple the speed, 9 times the energy. At everyday speeds, this barely matters. But at cosmic speeds, tens of kilometers per second, the squared term becomes catastrophic. A baseball moving at 20 kilometers per second carries the energy of a hand grenade. A boulder carries the energy of a nuclear warhead. No chemistry required, no reactions, just motion, converted to destruction on impact. This single principle, kinetic energy scaling with velocity squared, explains everything in this video. It explains why the dinosaurs vanished. It explains why a Russian city lost 1,400 windows on a clear February morning. And it explains why astronomers scan the sky every night hoping to spot something before it spots us. The story of humanity understanding this threat begins with a thin layer of clay. In 1980, geologist Walter Alvarez was studying limestone formations in Gubbio, Italy, trying to understand what happened at the boundary between the Cretaceous and Paleogene periods, the moment 66 million years ago when the dinosaurs disappeared. Embedded in the rock was a strange layer of reddish clay, just a centimeter thick. Something had deposited this material worldwide, simultaneously, in a geological instant. But what? Walter brought samples to his father, Luis Alvarez, a Nobel Prize-winning physicist who'd worked on the Manhattan Project. They measured the clay's chemical composition and found something startling. Iridium levels 30 times higher than normal rock. Iridium is rare on Earth's surface. It sinks toward the core when planets form, but it's common in asteroids and comets. The Alvarezes proposed something audacious. An asteroid, roughly 10 kilometers across, had struck Earth, vaporizing on impact, spreading iridium-rich dust worldwide, and somehow killing 75% of all species. The scientific community resisted. Where was the crater? The search took a decade. In 1991, researchers identified a buried impact structure beneath Mexico's Yucatan Peninsula, the Chicxulub crater, 180 kilometers wide, dating precisely to the extinction boundary, the smoking gun. But understanding that an impact occurred is different from understanding what it did. This is where velocity squared becomes horrifying. The Chicxulub impactor struck at roughly 20 kilometers per second. At that speed, kinetic energy calculation yields something like 100 million megatons of TNT equivalent, 1 billion times more powerful than the Hiroshima bomb. But the number alone doesn't capture what happened. The asteroid punched through the atmosphere in about 2 seconds, too fast for air to move aside. It essentially teleported to the surface. On impact, rock behaved like liquid. A transient crater 40 kilometers deep opened and collapsed almost instantly. Material ejected at escape velocity rained back down worldwide, re-entering the atmosphere as trillions of meteors. The sky heated to oven temperatures globally. Forests ignited. Then came impact winter. Dust blocking sunlight for years. Acid rain from vaporized rock. The collapse of photosynthesis. None of this required exotic physics, just mass, velocity, and that squared term doing its work. The dinosaurs died from arithmetic. That was 66 million years ago, ancient history. But the same physics operates on human timescales, and the evidence is disturbingly recent. February 15, 2013, Chelyabinsk, Russia. Morning rush hour. Dashcam footage from dozens of cars captured what happened. A streak of light, brighter than the sun, crossed the sky, hung for about 30 seconds, then detonated. The explosion released energy equivalent to 500 kilotons, 30 times Hiroshima. No one died, but 1,500 people were injured, mostly from flying glass when the shockwave arrived about 90 seconds after the flash. The Chelyabinsk object was tiny by cosmic standards, about 20 meters across, roughly the size of a house. It never reached the ground. Instead, it experienced an airburst. Atmospheric compression heated the rock until internal stresses exceeded material strength, and it exploded 15 miles up. Here's what's sobering. Nobody saw it coming. The object approached from the sun's direction, invisible against the glare. Telescopes searching for dangerous asteroids are essentially useless for anything approaching from sunward. This wasn't a detection failure, it was physics. Some impacts will always arrive unannounced. The Chelyabinsk event demonstrated something important about the kinetic energy principle. The rock massed about 12,000 tons. Its kinetic energy at entry was about half a megaton, but only a fraction of that, roughly 10%, coupled to the shockwave that caused injuries. The rest went into heat, light, and fragmenting the rock itself. Impact physics isn't just about total energy, it's about how that energy converts to destruction. Altitude, angle, material strength all modify the consequences, but the source is always the same: velocity squared. A century before Chelyabinsk, the same physics produced something larger and stranger. June 30th, 1908, the Tunguska region of Siberia. An explosion flattened 2,000 square kilometers of forest, 80 million trees knocked down in a radial pattern. The blast was heard 900 kilometers away. Seismic stations registered it worldwide. No crater existed. For decades, theories ranged from antimatter to a miniature black hole, but the physics eventually pointed to the same explanation: airburst. An object roughly 50 to 60 meters across, perhaps 3 times the Chelyabinsk size, exploded at an altitude of 5 to 10 kilometers. The energy release roughly 10 to 15 megatons, comparable to the largest nuclear weapons ever tested. Tunguska happened over unpopulated forest. Chelyabinsk happened over a city, but was smaller. The alignment of size and location has been lucky so far, but luck is not a strategy. So how do scientists actually find these objects before they find us? The basic method is surveying. Automated telescopes photograph swathes of sky repeatedly, and software identifies anything that moves against the background stars. Over 30,000 near-Earth asteroids have been catalogued this way. The largest, those over 1 kilometer, are almost completely mapped. Nothing currently threatens Earth for at least a century, but completeness drops dramatically for smaller objects. For house-sized asteroids like Chelyabinsk, perhaps 1% have been found. For Tunguska-sized objects, maybe 40%. These are the sizes that would devastate cities or regions without threatening civilization, frequent enough to matter within a human lifetime. The Torino scale rates impact threats from 0 to 10. 0 means effectively no chance of collision. 10 means certain global catastrophe. Most newly discovered asteroids start at 1 or 2 as orbits are refined, then drop to 0. Occasionally, one lingers higher for weeks before observations rule it out. The experience of watching a number refuse to fall is apparently unpleasant for those who track this for a living. Apophis provided a test case. When discovered in 2004, initial calculations gave it a 2.7% chance of striking Earth in 2029, the highest probability ever assigned to a known object. Subsequent observations eliminated the 2029 impact risk. On April 13, 2029, Apophis will pass within 32,000 kilometers of Earth, closer than geostationary satellites. You'll be able to see it move across the sky with naked eyes if the sky is dark, but it will miss, probably. The gravitational interaction during that close pass will alter its orbit in ways that depend sensitively on Apophis's exact shape and rotation. The post-2029 trajectory contains uncertainties that won't fully resolve until the encounter happens. Detection buys time, but what can actually be done with that time? In September 2022, NASA's DART spacecraft deliberately collided with Dimorphos, a small moon orbiting the asteroid Didymos. The impact changed Dimorphos's orbital period by 32 minutes, far more than the minimum expected. Kinetic impactor deflection works. Hit an asteroid years or decades before a potential collision, and a tiny velocity change compounds into a substantial orbital shift. But kinetic deflection requires advance warning, years at minimum, decades ideally. For objects discovered months or weeks before impact, the options narrow. Nuclear detonation could work, not to destroy the asteroid, but to vaporize surface material, creating thrust. This remains theoretical. No mechanism exists to launch such a mission on short notice. For objects discovered hours before impact, like Chelyabinsk, nothing can be done. The physics of launch, transit, and deflection require time that simply won't exist. So, where does this leave things? Return to that opening scenario. A car-sized rock, 3 hours from impact, carrying 30 Hiroshimas of kinetic energy. The energy comes purely from velocity, mass times velocity squared divided by 2. At 20 kilometers per second, even small masses become weapons. This isn't metaphor, it's the literal physics governing every impact in solar system history. The moon's face tells the story. Every crater records a kinetic energy transaction, mass met velocity, energy converted to excavation. Earth shows fewer craters not because it's been struck less, but because weather and tectonics erase the evidence. The bombardment rate is roughly equal. The Chicxulub impactor demonstrated what a large, rare event can do: end an era, rewrite biology, hand the planet to different inheritors. The Chelyabinsk object demonstrated what a small, common event looks like, survivable but capable of mass casualties through sheer bad luck of timing and position. Between those extremes lies a continuum of energies, probabilities, and consequences, all governed by the same equation. For 4 billion years, life on Earth had no ability to see impacts coming or do anything about them. Dinosaurs couldn't scan the sky. Trilobites couldn't launch deflection missions. Every species that ever lived simply accepted the bombardment as background noise, devastating when it struck, invisible until then. That changed in the last few decades. For the first time, life exists on Earth that maps the threat, calculates trajectories, and builds machines capable of altering them. The physics hasn't changed, but the response has. Whether that response will prove adequate depends on questions that haven't been answered yet. How much warning will the next dangerous object provide? What size will it be? Will funding for detection continue, or will the threat feel abstract until it isn't? The craters on the Moon aren't monuments to the past, they're a forecast. The only uncertainty is the date. If this was interesting, hit the subscribe for more and turn that notification bell on.